Hello, Physics 11. Here are the answers to the Week 3 Energy and Work quiz. Please feel free to move ahead to the questions that you did not get correct the first time around. So try that out for the ones that you didn't get, and I'll go through the solutions if you're not able to get them. So here's the situation. We've got a roller coaster going from part A along this flat part, going up the ramp at part B, reaching the top of part C, going back down to part D, and we know the mass of the mass of the cart is 8,300 grams. Okay, so for the first question here is it says it's going at 56 meters per second, and what is the kinetic energy? Well, I think just about everyone got this one right, and the answer here is we're just looking for this formula. So kinetic energy is 1 half mv squared, and this is going to be 1 half times 8,300 times v squared. Now v was 56 meters per second, so it's just going to be half times 8,300 times 56 squared. So we'll try that out. 5 times 8,300 times 56 squared. And that gives us 13,014,400, which I would accept any of those answers. I'm not too worried about sig figs. I think the best answer was 1.3 times 10 to the 7 joules, 2 sig figs for the answer. That'd be the best answer. But if you said 13 million, that would have also been acceptable because 13 million is 2 sig figs. So this is just probably the best answer. All right, what's the maximum height above A that would have been reached by the car if all the kinetic energy had been transferred to gravitational potential energy? So this is a hypothetical question. What it's asking is, we know the energy is conserved. So if we're saying all of the energy here, that's the key word, all of the kinetic energy, this amount of energy was going to be transferred into gravitational potential energy, what would that be? Well, you could simply take this answer that we already have, 3 times 10 to the 7, and this is going to equal the gravitational potential energy, so mgh, gravitational potential energy. You could have just gone that way, or you could have done this as a, doing full steps like we would have done in previous examples on previous videos. So EK equals EP. So EK initial equals EP final. And in this case here, we would have had 1 half mv squared equals mgh. The m's can cancel out, and essentially would have just solved for h. Now, if I go back to what we had before, because I know I already have the answer in my calculator of the kinetic energy, I'm going to divide this answer here. I'm going to divide this by 8,300 by the mass. And I'm going to divide that by G, 9.8. And that would give me 160. So that's what's left over for H. So what I've done is I've taken both of these and divided by m times G. And my H would be 160 meters. So that was the correct answer for part AII is 160 meters. This part here, it says it doesn't reach that height. So I did make this question out of one, but I was looking for two things specifically. So a lot of people got half a mark for this one. And essentially what it boils down to is these two words. So a lot of people got this word in here. So if you had it as a very short sentence, that would have been fine. But really I wanted to see this word first of all. Why doesn't it get the height? Well, because there is friction. Now, this is what the one that quite a few people got, friction, when they got a half mark. And the reason why it doesn't reach this height, though, if we're thinking about the unit, is because the friction leads to some thermal energy or heat energy being produced. So in order to see why it wouldn't reach that height, we would need to see that there is friction, yes, but the friction leads to thermal energy or heat energy or some sort of reference to that, and that's why it didn't get all of the final potential energy. So if you had the word friction and the word thermal energy, essentially that was full marks. However you put that into your sentence is fine, but as long as you had those two main ideas. There was friction in the system, and that led to the production of thermal energy, which meant that there was less available energy for potential gravitational energy. Okay, Part B, II. Car reaches point C at a height of 140 meters above A. So it's up here, and then the question is asking how fast is it going to go at D if 87% of its energy is converted. So a lot of people kind of ignored that 87%, and I think you got an answer of 52 meters per second, something like that. So let's just look at this as an energy problem. So sum of all the initial energy is going to equal the sum of all the final energy. In this case here, and we're saying 87% of its energy. So at this point here, we had initially potential gravitational energy, and in the end, we had final kinetic energy. But we didn't get all of it. What we got in terms of the end was 87% of its energy. So what we really had to do for this was just essentially multiply by 87% or 0.87. So that's all that it was essentially asking for this question. It didn't get all of the potential energy. It got 0.87 or 87% of the energy. So let's go to our formula. 0.87 times our gravitational energy. That's going to equal the amount of kinetic energy that we have left over. Should be consistent here. So that's going to be our kinetic energy that's left over. Again, the m's can cancel out. So we have point. So we have over here 0.87 times. I canceled out the m, so I'm just going to say 9.8 for g, and we're going to multiply that by the height, which is 140 meters. So that gives us the amount of kinetic energy, 1193 joules. There was more than that for potential. I guess that's not really joules because I've canceled out the m's. But nonetheless, that's going to be our value for m, or 1/2 v squared. So I'm going to multiply both sides by 2 over here. And that gives me my v squared value. So v squared is 2387. And I'm just going to take the square root of the answer there. And that gives me 48.8, or to 2 sig figs, 49 meters per second. So that would be how much energy we would have, or that would be how much velocity the object would still have when it got to the bottom of there. Now, once it reaches part D, it's on another horizontal section of track. So horizontal means that we're not worried about gain or loss of gravitational energy. It's just the kinetic energy that we're losing. And if we use this speed or this kinetic energy, either one really, what would be the braking force to stop it in less than 50 meters? And the hint I gave you was work done. And work done, remember, is just this formula. Work equals force times distance. And so essentially two options with this. You can just say, let's see, 0.87 times m, I'm sorry, m 8300 times g times 140. So this is the amount of energy. Now I think there might have been a few people who made calculation errors when they just ignored the 8300. So ignoring the 8300 works in this scenario here because you have an m on both sides. But if you look at force times distance and work, there is no m there. So just be careful when you cancel out m's. If you're dealing with work, you can't really cancel out m's all that often. And so this is the amount of energy that I'm going to have initially. So just to recap that one more time, what we're looking at here is if we're looking at this formula with what we do with work is we say the sum of the initial energy plus the work done is the sum of the final energy. So I've kind of skipped a few steps here initially. Let me just, hopefully this makes a bit more sense when I go over it a second time. The initial energy that we had, this was that remainder of the kinetic energy. So this kinetic energy was the 87% of initial potential energy. That's kind of how much kinetic energy it had based on this question here. So hopefully that makes sense. And if not, just pause the video and kind of think about that for a second. The amount of kinetic energy that it has, we're asking this question here, what's the amount of kinetic energy? Well, the amount of kinetic energy was 87% of this potential energy when it was up at 140 meters. So let's look at that amount here. That's our initial kinetic is 87% of the potential energy, plus the work done, and work done is going to be force times distance, and this is going to be our sum of our final energy. Now what we're saying is this comes to a stop and it's on the floor. So if it comes to a stop and it's on a horizontal section, so there's no change in potential energy, that means it's going to have zero potential energy and zero kinetic energy. It's not moving and it has no potential energy. So that's what this is going to equal. The final energy is going to be zero. Now hopefully this isn't too confusing. This energy isn't really zero. We know that energy can't be destroyed, but it's all going to be thermal energy. All of that initial energy in terms of potential and kinetic is all gone at this point. Now it's just that the track of the roller coaster has gotten a bit hotter. So now we're just going to solve this out essentially. So 0.87 times 8,300 times 9.8 times 140, that's my initial kinetic energy, plus force times 50 meters, that's going to equal 0. So let's do some math over here. 0.87 times 8,300 times 9.8 times 140. This is the amount of kinetic energy I had when it was at part C. This amount here, instead of being 13 million joules, something like that, it's just under 10, it's just under 10 million joules of kinetic energy here, and that's going to equal F times 50. So I'm going to bring both of these to the other side. I'm going to bring this, so minus 50F, and I'm going to subtract that over here, minus 50F. So that means this is going to cancel out. So this value here, 9.9 times 10 to the 6 equals negative 50 times F. I'm going to divide this answer here by 50. And I should make that by negative 50. So instead, this answer here will be a negative answer. Okay, so this is the force. So I wasn't too worried about the negative sign, but we should see that our force is going to be negative 1.98. Let's just call that negative 2.0 times 10 to the 5 newtons. That's my final answer, and it should be negative because it's going in the opposite direction of the distance. If the cart is moving to the right, but the force is to the left, and that would be considered a negative force. It's in the opposite direction of motion. We also know that it's going to be a negative force because, oops, what happened there? We also know it's going to be a negative force because it's doing negative work. It's taking energy out of the system. It did have 10 million joules, and then it had 0. So that must mean that there's negative work being done to subtract that amount. Nonetheless, this is the last answer, and if you have any questions, feel free to email me, or we can talk about it in next or in this week's tutorial.